The sorting of information is widely regarded as a fundamental problem of computer science. While divide-and-conquer algorithms dominate massive datasets, a seemingly basic approach holds the key to real-world hardware performance. This is the incremental paradigm.
Theoretical limits dictate that any deterministic comparison-based algorithm must perform at least omega of n log n comparisons in both the worst and average cases. However, this mathematical bound assumes random or adversarial data. Insertion sort circumvents this limitation in practice because real-world data is frequently partially sorted, allowing it to approach linear time.
Consider how you sort a hand of playing cards. You scan your hand from right to left, find the exact spot for a new card, and shift the others to make room. This is the incremental approach. It builds the solution bottom up, naturally accommodating data as it arrives.
Here is the core computational engine. Notice the inner loop. Instead of costly multi-step swaps, it relies on a highly efficient single right shift operation. This minimal data movement is a massive advantage on modern processors. Let us compare the exact cost of memory movement. A standard array swap requires 2 memory reads and 2 memory writes, as the temporary variable is stored in a CPU register. However, insertion sort uses a shift mechanism, requiring only 1 memory read and 1 memory write per shift, which still drastically reduces the overall bandwidth overhead. The mathematical profile reveals its secret weapon: adaptivity. While the worst case and average case scenarios both share a big O of n squared time complexity, the average case requires half the total operations compared to the worst case. Specifically, the constant factor drops from 1/2 to 1/4. More importantly, an already sorted array is verified in strictly linear time. We can define its performance precisely through inversion theory. Every memory shift resolves exactly 1 inversion. This means the algorithm's runtime is bounded by big O of n plus I, where I represents the number of inversions, meaning pairs of elements that are out of order.
Beyond theoretical notation, insertion sort possesses incredible mechanical sympathy with modern silicon. Its contiguous memory access pattern triggers CPU hardware prefetchers, flooding the L1 cache with hits. Furthermore, its simple inner loop results in minimal branch mispredictions when the data is nearly sorted, though highly random data will still challenge the predictor.
This raw architectural speed makes it the indispensable finisher for modern hybrid implementations. In bottom-up approaches like Python's Timsort, the system scans for naturally occurring sorted runs. It then utilizes binary insertion sort to forcefully extend them to a minimum threshold size. This binary variant uses a binary search to find the insertion point, drastically reducing comparisons, before efficiently merging those blocks. It is the ultimate tool for maintaining order in dynamic, memory-constrained, and real-time systems. In algorithm design, being the best is not absolute. It is a strict function of input size and data architecture.